Hello students, here is the question. We have two functions f and g which range from real numbers to real numbers, and we are defining them as x plus 2 when x is less than equal to 0, x square when x greater than equal to 0. Similarly, g of x as x cube when x is less than 1 and 3x minus 2 when x is greater than equal to 1. We need to find the points in R where f of g of x is not differentiable, meaning they can be continuous but their differentiation should not be equal, which are for the points x equal to 1 and x equal to 0. So what we do is we put the functions of g in the functions of f because we need f of g of x. And how we do that? We are going to look at the domains provided to us. Now the domain for x or in f of x is x less than equal to 0 for the first case, and for g of x it is x less than 1. Now g of x satisfies the domain for x less than equal to 0. So we put x cube in x plus 2 over here. So we get x cube plus 2 because we are putting the function of g in the function of f. So we get x cube plus 2. Or if we were doing g of f of x, we would get x plus 2 the whole cube. We are putting x plus 2 in the place of x in x cube. So over here, this is the other this is the different case, and we get x cube in the place of x, which becomes x cube plus 2 for x less than equal to 0, because these two domains satisfy the condition for x less than equal to 0. Correct? Now we have x greater than equal to 0 for f of x and x less than 1. So we have the domain that x is greater than equal to 0 for z x for f of x, and it becomes less than 1 for g of x. So the equation that we get is x square and x cube. We put x cube in x square, so we get x cubed the whole square, which becomes x power 6. Correct? Now we have x less than 1, but there is no other domain for f of x in this term, so we have made all the possible f of g of x for x less than 1 for g. Now we move on to x greater than equal to 1, which is over here. So x greater than equal to 1, if you put over here, this will not satisfy because we have x to be less than 0 in this case and greater than 1 in this case. So no function in over here has the same domain. So if we are looking for x greater than equal to 1 and this function over here, now if we look, we have x greater than equal to 1 and x greater than equal to 0. So we can say that f of x satisfies this inequality over here, that x can be greater than 1, which means x is positive, and x greater than equal to 0 also determines the same thing, only that it can have the values from 0 to 1 also. So what we do is we put 3x minus 2 in x square and we get 3x minus 2 the whole square, and the range is x greater than equal to 1 because we have it for x between 0 and 1, so we take it for x greater than equal to 1. Once we have all these ranges, we need to find which part is definitely wrong, so we need to differentiate it. And once we differentiate it over here, the RHD, that is the differential case, to check out the differentiability over here, here we can say that f of g of x is discontinuous at x equal to 0. If we put x equal to 0 in both cases, we get 2 in the left hand side and 0 in the right hand side, so discontinuous at x equal to 0. And if we look at non-differentiability at x equal to 0, we need to differentiate this, so the top term becomes 3x square and the bottom term becomes 6x raised to 5. So differentiable is not the case, because if the function is not continuous, it cannot be differentiable. But if the function is not differentiable, it can be continuous. So the differentiability does not imply differentiability implies continuity, but continuity does not imply differentiability. This is what we are proving over here. So once we have this case over here, we look at x equal to 1 because we have found out that it is non-differentiable at x equal to 0. So for x equal to 1, the right hand side is f of 1 plus h minus f of 1, f of 1 plus h upon h over here. So limit h tends to 0, we put the values in and we divide it by h, we get the value to be equal to 6 over here, because 3 plus 3h minus 2 is 3h plus 1, the whole square minus 1. Now if we do that, we get the values, and if we divide by h, will be able to get the value of RHD to be equal to 6. Similarly for LHD, we can do similar things over here. Now LHD, what we do for the denominator is we have h greater than 0, h tending to 0 positive, so it has a terms greater than 0, so we do that over here. Similarly, we use this and we put this term over here and we get this term over here, and when we simplify this enough, we get the value of 6 again. So the number of points of non-differentiability is only 1, because it is differentiable at x equal to 1 but non-differentiable at x equal to 0. Thank you.